Hey everyone, welcome back. So we've been talking about Earth science for the last couple of days. We started looking at the evolution of Earth and how scientists, specifically geologists, have actually been able to create a timeline of all the things that have happened in Earth's history. And how did they do that? Using their fossil evidence. If you remember what we looked at yesterday, with relative dating and absolute dating, scientists were actually able to paint a pretty good picture of how Earth evolved over the last 4.6 billion years, right? So what we're going to be looking at today is the more modern understanding of how our Earth is continuing to change. We saw how it changed before, and now we're going to see how does it continue to change, because every moment that we're here, it is changing underneath our feet. So how's that all happening? So this is going to be looking at the theory of plate tectonics. Strap yourself in. Let's go. All right, what's our date today? April 21st, 2020. Our topic is plate tectonics. We're looking at another 7th grade standard. Explore the scientific theory of plate tectonics by describing how the movement of Earth's crustal plates causes both slow and rapid changes in Earth's surface, including volcanic eruptions, earthquakes, and mountain building. Our goal for today, I will be able to explain the theory of plate tectonics and how it is supported through various forms of evidence. Keyword, right? When we're thinking about a theory, we've got to have our evidence. Our vocabulary, there's a lot this time. Plate tectonics, theory, continental drift, Pangea. I'll say that one again, Pangea, not Pangea. Continental crust, oceanic crust, convergent boundary, divergent boundary, transform boundary, and mid-ocean ridges. So ultimately, we're trying to get to answering this question. How can geologists predict events that will occur at convergent, divergent, and transform boundaries? So in order to be able to predict accurately, we have to be pretty grounded in the theory and the evidence to be able to then make predictions. So our check for understanding today, we're going to be watching a brain pop video, and then y'all are going to be taking the quiz that comes after that video. All right, so we are going to begin watching the brain pop video on plate tectonics. So as y'all are watching, I would like you to take your own notes in today's mission document. And when I pause to show you a question, go ahead and answer that question on your paper. Here we go.
Enjoy this movie, then visit brainpop.com for much more. Are you sure this thing is rated for this depth? You bought it from an Air Mall catalog. Oh, great. Dear Tim and Moby, when I look at a map, it seems like some continents fit together perfectly. Are my eyes playing tricks on me? From Georgia. You're not seeing things, Georgia. Some continents look exactly like puzzle pieces that snap together. Early mapmakers suspected that they were once all connected. In the early 20th century, a scientist named Alfred Wegener called this supercontinent Pangea.
So there's one of our first vocabulary words, Pangea, this idea that all of the continents were once connected.
He thought different chunks of it broke off and slowly moved apart. Over millions of years, they formed the continents we know today. Wegener couldn't explain why Pangea split up or how. But there was some evidence to support his idea. Fossils from similar plants and animals had been found oceans apart. The age and type of rock layers matched up too. Wegener's theory of continental drift provided an explanation, but his ideas weren't taken seriously until...
So there's our second one, continental drift. Go ahead and summarize on your handout. What exactly was his hypothesis? What was he theorizing?
Long after he died. In the 1950s, scientists began mapping the Mid-Atlantic Ridge. It's a mountain range running 10,000 miles along the ocean floor. Tests revealed that the farther you got from the ridge, the older the seafloor was.
All right, so our first question. What did the scientists discover on the seafloor at the Mid-Atlantic Ridge? So go ahead and write your answer on your note sheet, and then press play when you're ready. Okay.
So a geologist named Harry Hess proposed a revolutionary idea. New seafloor was forming at the ridge and spreading outward to make room for more. In other words, the surface of the planet was moving. Hess called this process seafloor spreading.
So what is he saying? Basically, that new Earth is coming up from this opening right here, and the sea floor is actually spreading. So what's coming up is actually the newer rock, and it's pushing out to the sides the older layer.
It seemed to indicate that rock was being forced up from inside the planet. Nowadays, we can see this rock formation in action. Wegener had guessed something like this, but he had no way to prove it at the time.
All right, our second question. How did he think this was happening? What was his evidence?
As he suspected, there's a lot going on beneath the Earth's surface. Up here, everything seems pretty cool and stable. But miles below our feet, it's a raging inferno. The deeper you go, the hotter it gets. Earth's center, or core, is as scorching as the surface of the sun. All that energy wants to escape like steam inside a boiling kettle. It pushes outward, putting...
What can we use to understand the extreme amount of heat produced at the center of the Earth?
Putting immense pressure on the middle section, the mantle. Standing in its way...
So for that previous question, what we can understand about the center is that there's a whole lot of pressure. So even though it's a liquid core, there's so much pressure that it actually makes it compact like a solid. So you don't have to write this out. I just want you to look at it. This is mostly a review. Remember that our center is the core, and then beyond that we have the mantle. What's important about the mantle? Good, we have flowing magma. It's actually liquid there. And then the very outer layer, pretty thin, is our crust.
Way is the lithosphere, a rigid layer of solid rock.
So what all makes up the lithosphere? That's our rock layer, our earth, our ground, basically the crust.
Well, the lithosphere isn't like a smooth shell. It's cracked into pieces, each one a different shape, size, and thickness. We call those pieces plates.
So what are the pieces called that make up the lithosphere? Ding, 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 plates.
Yep, the Mid-Atlantic Ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet. You can think of it like a pot of soup. The Earth's core is the burner, and the mantle...
What process do you think they're describing here?
...is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents.
If you got convection, give yourself a round of applause. All right, what makes convection currents turn in a circular motion? What is causing that to happen? Think about what we discussed when we looked at heat transfer. Heat does what, and cool liquid does what?
A similar process is driving the mantle, and it's taking the plates along for the ride. That movement is called plate tectonics.
So that's our big word. Let me rewind a little bit. Plate tectonics, right? This idea that our plates are actually in motion because of the convection currents in the mantle underneath that crust, underneath the lithosphere.
It's the engine driving the constant transformation of our planet's surface. Plates have been...
What is the engine driving our planets along the surface of the Earth? You got it, plate tectonics.
Have been bouncing off each other for eons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. The plates move about as fast as your fingernails grow, so we don't see the ground sliding around under our feet, but we do sometimes feel it. Yep, I'm talking about earthquakes. Seismic activity is greatest along plate borders, at convergent boundaries where two plates collide, at divergent boundaries where they pull apart, and at transform boundaries where they slide past each other.
Don't worry about this question. I just want you to notice the difference between the three. So convergent, if you take your hands and form them like a fist. Convergent, you're bringing your fists together and almost crunching them upwards. Divergent, you're pulling your fists apart. And transform, your fists are sliding past each other. Which one do you think is going to result in an earthquake?
At all three boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. Yep, and plate movement drives volcanic activity too. At divergent boundaries like the Mid-Atlantic Ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth.
What type of boundary is the most volcanically active place on Earth? Nice, the Mid-Atlantic Ridge, like they showed us before. It's right down along the Atlantic Ocean. There's live magma actually flowing out.
Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean plate converges with a lighter continental plate. The heavier plate gets pushed below, down into the mantle. Some of it melts, and the magma erupts farther inland.
Describe how subduction works. What did they just describe to us?
The Ring of Fire is a massive chain of these volcanoes. Dense sedimentary rock making up the Pacific seafloor is subducted, transformed into metamorphic rock through pressure and heat, and then recycled as igneous rock through volcanic eruptions. In other words, plate tectonics drives the rock cycle, the constant process of transformation and renewal of the Earth's crust.
So what is driving the rock cycle to actually take place? And the rock cycle is, like they're showing here, the recycling and reusing of different earth materials, rock layers.
It also creates our most prominent geologic features, mountain ranges. That happens when two continental plates converge. Since they're both about the same density, neither one subducts. Instead, it's like a slow-motion car crash. The plates buckle and warp. The land pushes up into jagged peaks. The Himalayas are still growing from a plate collision that began 500 million years ago.
What type of plates converge or collide or crash into each other to cause mountains to form? Was it divergent, convergent? Was it continental, oceanic? What type of plates? And like they said, they're still growing, even today.
Yeah, Alfred Wegener's theory has come a long way in 100 years. He was practically laughed out of the scientific community for his ideas. But today, plate tectonics is the unifying theory that ties together the entire field of geology.
So I want you to think about what new evidence were scientists able to gather that kind of supported Wegener's initial theory that these plates shifted and moved away from each other in his theory of continental drift. What new evidence did scientists get that supported that theory?
What do you mean, out of juice? We're stuck here? Now what? Oh, thank you. Visit us at brainpop.com for more on this topic and hundreds of others.
All right, nice. So if you needed to go back to the video at any point, just rewind, pause, fill out your note sheet, and then continue watching.